I think we might actually go ahead and get started if that's okay with you guys. So my name is Sarah Giles. I'm a PhD student at Columbia University in New York. I put together and will be hosting these talks today from three wonderful student presenters. They will be presenting on the impact of climate change on sedimentation. So before we get started, I'd like to thank our sponsorship from IAS, which makes all of these resources free of charge. So please go check out our website. There's coffee breaks, there's more presentations, past presentations, student webinars you could check into. And so please check this out if you have the time. So today's webinar, like I said, we'll have 3 student presentations. They'll be 10 minutes long. And after each presentation, we will have 5 minutes for questions. If you can please put those in the chat with your name and where you're sending your question from, and also the student who it's for. I'll read those out to the student and they'll answer. If we don't get to all the questions in the 5 minutes for that student, I'll take note of them. And at the end of all the presentations, we'll come back and answer those in a student format, in a panel format. So without further ado, I'm going to stop sharing and have our first presenter, Fatemeh Izaditame, a PhD student from the University of Delaware, will be discussing contaminated sediments. And I'll let you share your screen and if you can get started for us. And I'll let you know, make sure that your presentation looks good. Yeah, looks great.
Okay. So can you see my screen?
Yes, your screen is good to go. You can start whenever you're ready.
Okay. Hi, everyone. My name is Layli, and I'm a PhD candidate at the Environmental Soil Chemistry Lab of the University of Delaware. And today I'm presenting a part of my research on how climate change-induced flooding can impact the fate and speciation of arsenic in contaminated coastal sediments. Let's start with a short introduction. As we all know, sea level is on the rise due to climate change. And according to the Intergovernmental Panel on Climate Change 2021 report, we expect to have around 1 meter of sea level rise by 2100. Global mean sea level rise is about 3 millimeters per year. However, sea level rates in the mid-Atlantic coast of the US is surpassing this global average because here we have a dual impact of coastal subsidence and sea level rise. Sea level rise is an important issue affecting the life of a big proportion of the global population. According to the United Nations, about 45% of the global population, including 40% of Americans, live along the coast. So the anticipated sea level rise by 2100 would put the homes of almost 8 million Americans at risk of being flooded. What makes sea level rise even more important is the fact that contaminated sites are in the areas that may be impacted by flooding or sea level rise. Federal data suggests that about 60% of Superfund sites in the United States are in areas that may be impacted by different types of sea level rise induced flooding. Here we are looking at the Naval Station Norfolk at its current and higher sea levels during the type of storms that hits on average once a year. This highlights the correlation between sea level rise, flooding, and important coastal sites. The history of industrial activities has left a legacy of arsenic concentration in many coastal soils, including Delaware coasts. Through natural attenuation processes in the soil, such as sorption and precipitation, this historic contamination has been stabilized over time. However, changes in environmental conditions, such as climate change and sea level rise, can result in shifts of arsenic speciation and mobility. In solution environments, inorganic arsenic species are mostly available in arsenic 3 and arsenic 5 speciation format, with arsenic 3 being the more toxic and mobile arsenic species. Arsenic is a well-known carcinogen toxic, which is associated with the skin, lung, bladder, and other internal organ cancers. And the goal of my research is to evaluate the release and partitioning behavior of sediment-bound arsenic during sea level rise-induced perturbations. This map shows Delaware and its 0.5, 1, and 1.5 inundation zones. The red dot over here is the location of my case study at a contaminated site in coastal Wilmington, Delaware that falls within 1 meter sea level rise inundation zone. The site is adjacent to Superfund sites, landfills, and waste generators and has elevated amounts of arsenic. For this research, we collected 3 sets of sediment samples from the site with different arsenic contamination levels. The first group of samples were collected from the banks of the Christiana River, where we found 900 milligram per kilogram of arsenic. The second group of samples were collected from the banks of a tidal beach, which was constructed as a part of a remediation effort for a neighboring US EPA Superfund sites, where we surprisingly found 5 to 6% of arsenic in sediments. These samples were used in 3 sets of experiments to study the concurrent impacts of sea level rise induced flooding on arsenic concentration and speciation in solution and solid phases for the first time in the literature. To run the experiments, we used a specific reactor that is specifically designed to mimic flooding conditions in the lab. The reactor has the potential to impose different levels of shear stress at the sediment water interface that are representative of flooding events with different intensities that can happen in natural environments. 3 sets of experiments were set up using each collected sediment, and the system was inundated with filtered river water. Each experiment had 3 phases where we monitored system before, during, and after flooding events. Here we are looking at just one experiment as an example. During the benthic flux phase, we monitored the system for 7 to 9 days before we imposed the shear stress at sediment water interface. Reactors were then imposed to different levels of shear stress during the erosion phase, and the systems were further monitored for 4 to 7 days during the post-erosion phase. Water samples were taken at different time intervals during each phase and were filtered to separate particles. Then arsenic concentration and speciation in solution and solid phases were determined using HPLC-ICP-MS and arsenic X-ray absorption spectroscopy. In this presentation, I will only present the results for the solid phase. Here we are looking at the arsenic bulk Zanes analysis and the linear combination fitting results showing the speciation of arsenic in the collected natural sediments. We use sodium arsenate and sodium arsenite as standards, and we found a mixture of arsenic 3 and arsenic 5 in natural sediments collected from the beach and riverbank area. Here we are looking at fine scale micro XRF mapping on the untreated sediment that is showing a collocation of arsenic with iron, calcium, zinc, and magnesium in the natural sediments used in tests 1, 2, and 3. Here I'm presenting arsenic bulk Zanes analysis and linear combination fitting results for tests 1, 2, and 3 during the erosion phase of the experiment. On the y-axis, we are increasing the shear stress in different tests, and we are looking at the speciation of arsenic under resuspended particles. The 2 bottom spectra represent sodium arsenate and sodium arsenite, or our standard, and their white line positions. As you can see, the results, the original sediments and the sediments resuspended at the highest shear stress levels are very similar to each other and gave pH features that is indicative of the presence of arsenic 3 in the sediments. It is maybe because when shear stress is imposed, it initially oxidizes arsenic 5 in the sediments to arsenic 3. However, over time, when more anoxic sediments drops off, we will have more arsenic 3 in the resuspended particles as they are coming from more anoxic layers. Moreover, the water column is less oxic compared with the initiation of the shear test when we increase the shear stress at the sediment water interface, and some arsenic 5 can be converted to arsenic 3 over time. During the post-erosion phase of the experiments, the ratio of arsenic 3 to arsenic 5 in our resuspended particles were very close to that of the original unaltered sediments. And the concentration of arsenic on resuspended particles, as can be seen here, was decreasing during this phase. And arsenic was still mainly collocated with iron during the post-erosion phase. Flooding not only impacted arsenic speciation in the solid phase, but it also affected the morphology of the sediment, as can be seen in these SEM images. Here we have the original sediment, the sediments resuspended at lower shear stress levels, and the sediments resuspended at high shear stress levels, and the sediments remained suspending in the sediment after the flooding events. And we can see that by increasing bottom shear stress levels, we can see the formation of these rod-shaped structures at the surface of the resuspended particles. We think that this rod-shaped structure may represent the formation of some bacterial communities that control the release and scavenging of arsenic at different shear stress levels. The same similar observation was previously reported in the literature by, for example, Moret and Callas in 2006. Now, for example, the abiotic oxidation of arsenic 3 and iron 2 may have led to the precipitation of mixed iron 3 and arsenic 5 hydrous oxides at lower shear stress levels, and that's why we had more arsenic 5 in our resuspended particles at our lower shear stress values in our experiments. Now I'm going to summarize our observations. We observed that sea level rise induced flooding can increase arsenic concentration in solid and solution phase. At lower shear stress level value conditions, we observed that we are having more arsenic 5 in the resuspended particles, or more conversion of arsenic 3 to arsenic 5, and this may be assisted by bacterial activities, we hypothesize. At higher shear stress values, when we are dealing with more anoxic systems, we think that iron reduction can be accompanied by the reduction of arsenic, which can lead to the release of arsenic, soluble arsenic to the system. Arsenic concentration was decreased in our resuspended particles during the post-flooding phase, and considering the mass balance, we believe that it should increase in the solution phase. And our solution phase data confirms this hypothesis. And therefore, our results show that climate change and sea level rise induced flooding has the potential to cause arsenic release from contaminated coastal sediments, not only during the flooding events, but also after the flooding and in post-flooding phase of the experiments. With that, I would like to thank my research group, specifically Dr. Donald Sparks for his supervision and support, my funding sources, and all of you for your time and consideration. For those interested in knowing more about my results in the solution phase, you can go and take a look at my publication, in which I completely reported all the data for the solution phase. And I would like to thank you and would be happy to take any questions and suggestions.
Thank you so much. That was wonderful. You've done some really exciting work and such an interesting conclusion. I have a question for you, but I'm going to first get to, I think this is Val's question here for you. And anyone, please just put your questions in the chat with your name and your location, and I'll read it out. So this one says, very interesting talk, Valentin here from Germany. Since we can also expect an increase in salinity upstream of the mouth of these rivers as the sea level rises, would this increase in salinity influence the redistribution of arsenic during and after flooding events?
I think that's a really interesting question, and that's a part of the experiments that I'm planning to do to have a more concrete answer for such questions. So I'm going to have some experiments in which I specifically consider the dual impacts of salinity and shear stress and the release of arsenic. But like if considering the pure impacts of salinity, I can say that it's gonna still cause a more release of arsenic to the water systems.
Excellent, thank you. And I'll come in with my question here. I was wondering if you've taken a look at all with the sea level rising, is there any spatial differences in the arsenic concentration, along a coast, or, would you ever look into that? And would you have any expectations?
I have not specifically taken a look into that, but like the three sets of different samples that we collected has had a lot of difference. Like the ditch area and the area that are adjacent to the Superfund sites in Bloomington are highly contaminated. But even the concentration of arsenic in the riverbank, which is just like in walking distance from the Superfund site, is still very high, but like in the orders of magnitude lower than the Superfund sites area. So there is a spatial difference in arsenic concentration in the area, I can say.
It's really interesting. Thank you so much. Well, in the interest of time, we will move on to our next presentation. But if there are any questions you would like to ask, please put them in the chat and we can revisit them in a panel at the end. So next, we will move on to our second presentation from Valeria Ruscitto, a PhD student from the Sapienza University of Rome, who will be discussing her work looking at shallow water archives. So feel free to go ahead and share whenever you can. Perfect. Thank you so much, Valeria. If there are any more questions, we will definitely return to them at the end. I think for now, to stay on time, we will move on to our next presentation, which will be from Matthew Staitis, a PhD student from the University of Edinburgh, who will be discussing the sedimentary record of ocean acidification.
Okay, thank you very much. I'll just show my screen. Okay. Yeah, everyone's seen that now?
Yep, looks great.
Okay, great. Right, okay, thanks everyone, and thanks for coming along to my talk today on this really interesting question where we're scratching our heads really because our sedimentary evidence isn't really agreeing with what we think is going on in the rock record. So today I'm going to speak about assessing the sedimentary record of ocean acidification prior to the key PG mass extinction. That's that famous extinction of the dinosaurs 66 million years ago. And you can see this beautifully exhibited here, the boundary here between the Cretaceous and the Cenozoic is a very big color change in our deep ocean sediments. But as you can see, there's a lot of questions about, are we seeing any environmental signals prior to this extinction event? So this work was done with myself, but also my primary supervisor, Professor Dick Kroon at the University of Edinburgh, and also my co-supervisor, Dr. James Barnett at the University of St Andrews. And okay, so move on. So ocean acidification in the sedimentary record. So we're going to step back even further than our previous speakers, all the way back to the earliest Cenozoic, the latest Cretaceous in the earliest Cenozoic. This is, 67 to 40 odd million years ago. And what we can see in our diagram is a compilation of different data sets. We've got sedimentary data sets at the bottom here. We've got the sedimentation rate within our deep sea site and our changes in the amount of iron intensity in our deep sea site. And we also have a geochemical proxy, delta 18O, which is a proxy for temperature. So these peaks correspond to global warming events. And I think when most people think about these deep sea sites and ocean acidification, the sedimentary evidence typically is this if we look to the left here, this core shows this very abrupt change in the calcareous nanofossil ooze. This cream color changes abruptly to a brown clay, and then which symbolizes the onset of these warming events. Rapid declines in calcium carbonate, rapid increases in the amount of iron represented in our clay. And then after our event, we have a recovery of calcium carbonate and a return of the iron. So traditionally, this has been used to identify these events in the geological record. And you can see that there's several of these events during the greenhouse climates of the early Cenozoic. And this, for example, is the infamous PETM event, which is a poster boy for paleo-ocean acidification events in the geological past. Interestingly, though, not all of these events seem to meet this kind of criteria. So this is one event I looked at in great detail, the late Maastrichtian warming event, which just precedes the Cretaceous Paleogene boundary 66 million years ago. What we can see here is when we zoom in to this event, just at the end of the Cretaceous, we see a rapid increase in temperature, but we don't see the characteristic increase in iron. We see a very variable signal, these large increases and decreases in iron intensity. And this has actually led some authors to speculate that there's a lack of sedimentary evidence to suggest an ocean acidification event accompanied this rapid increase in global temperatures 66.34 million years ago. Interestingly, when we look to the sedimentation rate in the core, we actually see something very odd. We see very increased sedimentation rates during the onset of the event, very different from the PETM that I showed just previously. So something very different is going on here and during this event than the other later hyperthermals of the Cenozoic. So what exactly is going on? This is quite interesting as well, because this core, ODP 1262, which is a very famous core just around the position of where we have a lysocline in the deep sea during most of the early Cenozoic back into the latest Cretaceous, is a really good place to look at shoaling of the lysocline and really identifying these hyperthermal events that characterize the climate of that time. And what's very interesting is the material from this core has been used by authors to evoke a causal link between that other environmental perturbation prior to that asteroid impact 66 million years ago, the Deccan Trap volcanism in present-day India. And it's believed that there's a correlation between the Deccan Trap outgassing of this large igneous province and this warming event, the late Maastrichtian warming event right here. And as authors have used various lines of evidence to suggest this, you can see that the warming event here in the blue doesn't coincide with a peak eccentricity maxima. It actually starts during an eccentricity minimum. What that simply means is that the warming event occurs when the Earth is furthest away from the sun, which is not what you would expect if it was orbitally induced. Also, interestingly, unlike other warming events like the PETM that we just saw, that are accompanied by very large negative carbon-13 excursions, like this, which the red graph here shows, we actually see for the late Maastrichtian event a very unusually muted signal. We see a small negative decrease here, but nothing as substantial as other hyperthermal events as well. And this is what some authors have used to interpret as a heavier mantle source of CO2. So if this was Deccan outgassing of large volcanism, why aren't we seeing the global acidification in the core? Which was a very interesting point to make. So actually, perhaps our sedimentary information is biased in some way. So there are other factors that influence the percentage, the amount of iron or calcium carbonate in the core. For example, potential bias in iron could be introduced due to variations in the flux of wind-blown aeolian dust from nearby African continent, where which is 1262, the site, deep sea site's just located off the coast of Africa. So it's potentially that maybe there's influxes of dust that are coming in and skewing our records. Also, likewise for the calcium carbonate, interestingly, perhaps the hyperthermal warming that we're seeing is actually causing more stratified oligotrophic surface waters. And in its environments like this, in this picture here, we can see that large blooms of coccoliths like to proliferate in. So perhaps we're seeing increases in sedimentation due to warming rather than rapid declines in the amount of calcium carbonate due to acidification. So it's very complicated. It's not as straightforward as we might think. So how do we solve this problem? So this is where my work came in, and it was to really look at applying some novel trace element geochemistry alongside these these lines of sedimentary evidence to really start to piece together what exactly was happening during this event. So the geochemical proxy I used was the boron calcium trace element proxy. This proxy really works almost like how this diagram here shows. We see that in a given scenario, we have large volcanism releasing large quantities of CO2 into the atmosphere. You would expect the CO2 to then be absorbed by the oceans. And as a result, you would see a decrease in the ocean's pH, or increase in ocean acidity. And the ocean chemistry starts to change as well. We see a decrease in something called borate ions. And this is actually been shown to be recorded within the ratios of boron and calcium within the calcite tests of benthic foraminifera here. So potentially, we should also be able to get a more high-res geochemical signal for decking outgassing and ocean acidification, even if our sedimentary evidence suggests otherwise. Because what we'd also expect to see in this scenario would be an increase in the lysocline. So the lysocline is that chemical gradient that determines the preservation of calcium carbonate over clay. So a shoaling or a shallowing of the lysocline, we would expect to see a decrease in calcium carbonate and an increase in ion intensity within the core. So therefore, the hypothesis would be that boron calcium trace element record would show ocean acidification occurring during the slate Maastrichtian warming event in ODP 1262. So to get there, how did we get there? Well, the cores were first recovered by, it was an ODP leg 208 back in 2003, 2004, was able to drill down quite deep and recover these excellent preserved sedimentary records. The bulk samples were later collected by my co-supervisor and stored away for many years. And it was only during this project that we were able to get them out again and really start to look at them differently with some geochemical evidence, which then included foram picking for the benthic forams under a binocular microscope. And then the forams were then collected and crushed, cleaned and dissolved and ran on this fancy mass spectrometer here, this triple quad ICP-MS at the University of St Andrews. So what did we find? And this is what's really quite got me interested here. So what we have here is the trace element records for two different benthic foram species. And what our data really shows is we do actually see within the geochemical data this gradual progressive decline in the ratio of boron to calcium, which, as we know now, shows a decline in either oceanic pH and or increased inorganic carbon in the deep ocean. And this kind of marries up very nicely here to this almost muted negative decrease here that we're seeing in the the negative carbon-13 isotope excursion. And we can see that this event was, a 40,000 years potentially decline, and then followed by a period of perhaps just over 100,000 years of outgassing and low oceanic pH conditions at 1262 at least. And although we had that unusual high amount of sedimentation rate and high amount of calcium carbonate within our core at 1262, our data is in fact backed up by other calcium carbonate percentage data sets from the same interval at other deep sea sites. We actually see that where we see our decline, where we expect our oceans to start to becoming more acidic, we are seeing, for example, in ODP 690, a decline and a very abrupt decline in ODP 1403. These sites are in higher latitudes, but we see that actually we're seeing the event at kind of shallower paleo depths and very deep paleo depths. So perhaps it's just a local signal here causing the variability within 1262. Question is, what is that local variability? Well, authors have actually, using spectral analysis, have actually been looking to tie these iron maxima excursions that we see here to some sort of orbital signal. And in fact, authors believe that these iron maxima, these spikes in the iron record that we're seeing, are actually driven by transient precession cycles every 21,000 years, which we can see here. Every time we have a precession cycle coming in, we're seeing a peak in the iron intensity. And this is only because I think under higher climate sensitivity, under the warming event, we are seeing these peaks in the iron. On to my final slide just there, just running over briefly, but we actually are seeing that these negative decreases within the boron calcium record are corresponding nicely to several of these iron maxima. And we actually believe that this is showing precession export productivity, enhanced burial and remineralization of light carbon, which is then causing, as a result, decreases in the records here in relation to decreasing pH. So yeah, I'd like to stop there and happy to take any questions as well.
Thank you so much, Matthew. That was wonderful. And it's really, really interesting. I think that's, I always hear the contentious discussions around it. So it's really cool to see your new work and new results on that. I think while we wait for some more questions to come in, you know, it seems like you're at the end of this work. If you could apply anything else to kind of further test what you've concluded, or, you know, throw something else at it, what would that be?
Yeah, I think one of the major things in terms of the sedimentary record is that we've kind of got that's really, we're pushing the limits of what the sedimentary record can really tell us. But I think really some where the debate kind of currently is unresolved, as well as what did this do to life at the time as well, just before that impact event with the at the end of the Cretaceous, and could we potentially see changes within you know, the forearm populations, or what else that we're currently seeing in some well-studied PETM sections as well. So I think, you know, potentially looking at bringing in some micropaleontology in there, or other sedimentary records potentially that are showing maybe maybe even going back and having a look at, you know, sedimentary sections which are showing increases in iron, calcium carbonate, but low iron or variable iron, which we've just assumed is not, maybe there's hidden acidification events in there that we've just not realized through the sedimentary record. So maybe going back and using some geochemistry to see, are we seeing a different signal as well? And also thinking about our sites as well, like when we go and plan these ocean drilling legs, are we considering other local environmental biases, you know, aeolian dust or changes in productivity as well, that plays a role. Yeah.
Yeah, I think that was going to be my follow-up question is, you know, for these local controls on some of the variations, maybe, or maybe a reduced signal in some of the boron or things like that, you think it would be like aeolian dust or productivity? Why would you think aeolian dust would add a big contribution?
Yeah, but because I think what's been suggested by previous authors at this site is it's due to its proximity to the African landmass, and Saharan dust potentially could, you know, bring in a large quantity of iron into the site, which might skew some signals. But I think what's quite evident is that the signals are quite evenly spaced. They're quite almost periodic, which looks like maybe more of an orbital signal. And I think that this data from the geochemistry actually supports that. But what's interesting is that whereas we would imagine it to be transient releases of light carbon, almost like carbon burps, due to either volcanism or other kind of terrestrial deposits being destabilized like permafrost, we're potentially seeing that this event actually did, in the 1262 site at least, really increased sedimentation rates through this kind of oligotrophic almost coccolithophore bloom loving conditions, which actually increased calcium carbonate in the ocean acidification signal from a sedimentary perspective anyway. It was almost skewed and kind of lost. So that confused us for many years. But I think what we're seeing now that is it's actually due to the rate of carbon release. With the PETM event, we're having a very rapid release of carbon, somewhere between 3 and 20,000 years, whereas we're seeing with the late Maastrichtian event a rather protracted 100,000 years or more slow release. And as a result, I think the Earth system is buffering that, and we're not seeing the sedimentary record showing what we'd expect under other conditions. So I think there might be some questions.
Yeah, so you got a few questions here. So we'll start with one from Val, who asks, he says, killer analyses, Matthew. Not an expert, he thinks this might be out of topic, but he says, the Deccan traps seem to be the trigger of the LMWE, but why did it cool down before the end of the Deccan traps? If I'm totally wrong, don't hesitate to say that.
No, definitely, and that's a very good question, Val, by the way. That's, yeah, it seems to be that at the very end of the Cretaceous, the climate system was operating, there was lots of different players at work, as it were. So we had the Deccan traps, and we believe that some of the most earliest emplacements of the Deccan traps correlate to around about 340 odd thousand years before the asteroid impact. And some recent work from the geochemistry of those basalts actually show that they are more volatile rich. They're more rich in volatiles like CO2, for example. And in fact, that we might be seeing that the earliest phases of the Deccan traps released the most CO2 most abruptly. And then these later, larger emplacements of the Deccan traps throughout the impact and post-impact are actually not outgassing as much CO2 as the earliest earlier emplacements. In terms of the trigger and why it cooled down before the Deccan traps, I think mostly I think there's something to do with these earliest emplacements were more volatile rich. The later ones were not as volatile rich or didn't outgas as quick. And I think there was, as we can see, there definitely seems to be some orbital control here. And I think we're coming, by the end of the late Maastrichtian event, we're kind of coming out of our 405 or eccentricity maxima, these orbital changes on different timescales. And I think we're coming out of one of those as well. So I think together that's driving the decrease, the cooling that we're seeing just before the impact. Yeah.
Thank you. So we have a question here from Irene from Pisa, Italy. She says, congratulations on your great talk. I have a curiosity. Why did you choose benthic forams instead of planktonic? Do you expect different results within different portions of the water column, surface versus deep?
Yeah, that's a good question. I think in terms of the site that we got the samples from, it's quite a deep site. So we did hope to run some planktics as well. But what we were experiencing was that due to the changes, we got this site's quite deep, 3,000 meters. So planktics that are living in the surface waters, when they're coming down and settling on the seabed, they're actually remineralizing and experiencing some diagenetic overprinting. So we did try and run some planktics, but unfortunately for the site that we had chosen, it was just too deep, and the signals were getting lost. I think there is, however, some new planktic data coming out. My co-supervisor, James Barnett, is producing that as part of his postdoc. And I believe that other shallow water sites, like we heard in previous talks, could be a good place to answer this question. But I do think that I think we need to consider, as I've said, site-specific conditions, what's driving sedimentation during these events, and also is the signal out there in other places that we might have overlooked. But yeah, I think the planktics might show this as well. You need to find a good section somewhere, shallow water section, that you can have to do that analysis on.
So we have a follow-up question from David here on Val's question, saying, and why did the response of your iron signal so expressed during that specific eccentricity cycle and not the one prior to that?
Yeah. So that's another thing that's been confusing authors and a lot of us when working on this, was exactly why the looking at. Am I looking at the right question? No, sorry, there it is, David. So yeah, sorry, I was looking at Ross's question. Sorry. In relation to the ion signal expressed during the specific. Yeah. So why are we seeing the large increase in the ion maxima at the one precession eccentricity cycle, not another? I think that's also due to the influence of the climate sensitivity being heightened by the Deccan outgassing. I think, as we can see, prior to as we saw, that there is these precession peaks, but the peaks actually increase quite largely just after the onset of Deccan volcanism. And I do believe that's something to do with the outgassing of the Deccan volcanism, increasing climate sensitivity, and as a result, our eccentricity cycles are being enhanced by that. And I think that's why. So in a way, yeah, I think that's why previous eccentricity cycles, we were seeing a increase in iron, but nothing as large as the increases during the late Maastrichtian event. I think that's solely due to the climate sensitivity increase due to the outgassing of the CO2.
Thank you. And then we will follow up with Ross's questions here, who says, thank you, Matthew, intriguing stuff. Do you know the iron mineralogy? The iron speciation proxy could help define bottom water chemistry. Could it be an upwelling signal and increased bottom water anoxia and pyrite deposition? And that's from Ross in Canada. And he also says, P.S. you should be able to identify aeolian grains optically.
Yeah, well, this is some good stuff here, and this is some really interesting ideas. So yeah, I mean, these techniques definitely could help decipher some of that, what exactly is driving the variations in the iron and the calcium carbonate. Is it in fact aeolian grains, or is it not? Is it just simple clays in the deep ocean? But yeah, I'm off the top of my head, I'm not entirely clear on the iron species, what exactly the type the iron is. Do we see bottom water anoxia and pyrite during this event? No, we don't, which is another interesting thing, because a lot of these earlier Cretaceous warming events are associated with an ocean anoxic and pyrite deposition, but we are not seeing that for the for this event. So yeah, that's a very interesting point. Why exactly that is, I'm not entirely sure. I think again, it must be due to perhaps early in the Cretaceous, we still had a lot of enclosed, restricted basins. The Atlantic was still quite narrow. By the late Cretaceous, seafloor spreading was quite, I think from memory, quite widespread. And I don't know, I think there might be, again, anoxia has varying local tectonic factors to enclose your basins, whereas I think by this time we had a more kind of more widespread ocean basins and circulation, and I think we just did not have anoxia just taking place. We do have some signals of potential anoxia in the higher latitudes around in Antarctica. There's been some sulfur studies, but I don't know, again, that might be more local than global, than our global OEE events in the mid-Cretaceous. So yeah, no, I don't think we're seeing anoxia in this event. I think this event's maybe a wee bit more similar to the later Cenozoic hyperthermals like the PETM, where we're getting this kind of outgassing and maybe orbital control.
Perfect. Thank you so much, Matthew. And thank you to all of our wonderful presenters. I think we will wrap up for this week. Please stay tuned for our next student webinars. And if you know of any great students or professors, please nudge them to present with us, and stay tuned for the next topic that we'll present. But let's give a huge round of applause for our amazing presenters today, all with really fantastic topics looking at climate change and its effect on sedimentation. So thank you. We will close out, but if our presenters can stay on, I think we'll want to give you a few more thanks after.